Hello and welcome to this presentation on chemical engineering at Imperial College. My name is Clemens Brechtelsbauer. I'm the Director of Chemical Engineering Education in the department, and together with two other colleagues, I have the responsibility of managing the undergraduate course, which is what you are interested in for today. Right. The content of the presentation is first, I'd like to give you a brief outline what is chemical engineering, tell you something about the department, describe the different course options we offer, tell you a little bit about our teaching and the curriculum, what you will learn, present our research to you, and then we'll talk about admissions and scholarships. Now, first of all, what is chemical engineering? Now, chemical engineers work very closely with chemists, and a chemist will always look for the best solution to a problem. Now, a chemical engineer will look for the best possible solution to a problem within the available time and resources. So an engineer introduces the time dimension into this problem. What do chemical engineers do? Now, chemists develop new molecules, new processes to make these new molecules. And chemical engineers then take these chemicals prepared by chemists and design processes that produce them on a larger scale, safely, environmentally friendly, economically, and last but by no means least, multidisciplinary. It is very likely that when you work as a chemical engineer in industrial practice, that you will have to work with other scientists, other engineers. You will most likely not work with a lot of other chemical engineers. You will represent chemical engineering to them. Now, an example. I hope most of you may recognize this rather stern-looking gentleman who is quite famous for his connection with Imperial College and discovering something strange in his petri dish one day, which is of course penicillin, and the gentleman is Sir Alexander Fleming. Now everybody, almost everybody, has heard of Alexander Fleming and penicillin, but Alexander Fleming, although a very brilliant scientist, wasn't necessarily interested in turning penicillin into a product, into a medicine. That fell to someone else. And that, what you can see here on screen, is the first product that was made with penicillin powder, which was delivered to Allied soldiers in World War II, because penicillin, of course, is a drug against infections, an antibiotic, and a lot of the casualties in wartime is not just because of the immediate effect of exposures on the battlefield and wounding, but of the infections that set in afterwards. And the person who was responsible, who led the team to make this first product, is this gentleman. And I'm sure probably no one of you has heard of him. His name is Jasper Kane. He's was an American chemical engineer who pioneered the process of making penicillin called deep tank fermentation. And he did all that with his team in a disused ice cream factory in Brooklyn, in New York, in the 1940s. And within 6 months, he converted the process, or the laboratory process, which was surface aeration, very difficult process, very unreliable, and he developed with his team a new process called deep tank fermentation to make penicillin at a large scale. And this process that he pioneered with his team is still the standard of making antibiotics today. And Jasper Kane had a very distinguished career in industry, and he later on became chief executive officer of the company that he was working for at the time when he developed penicillin. And you may have heard of this company. It's called Pfizer Pharmaceuticals. Now, how do chemical engineers do this? Now, chemical engineers use models to describe the transformation of mass and energy in these processes, not those models. No, not those models either. I'm afraid it's those models. And that is usually where the sharp intake of breath can be heard in the audience. It's fairly complicated mathematics we're talking here about. But these models allow us to predict the behavior of systems at a larger scale. And then we can generate, for example, response curves that are shown here on the slide. So in short, we want to go from the laboratory with the Erlenmeyer flask and the round neck flask. We want to go to an industrial plant that looks like this and makes products at a large scale for everyone. Because if you think about penicillin, if penicillin had been a laboratory oddity, it may have benefited maybe a handful of people just in a laboratory, but it would have never made a medicine. And now, because it has been transformed from a laboratory process into an industrial process, then it can help millions of people. And penicillin and the derivatives of penicillin have saved millions of lives since the 1940s. Now, what does it take to become a chemical engineer? Now, it's not the ability to give up your social life, although that might come in handy. I'm just kidding. You need to have a strong background in mathematics. You need to be very interested in sciences, and you need to be very good at communicating. It's essential because all of our work happens in teams, in multidisciplinary teams, that you're able to explain what you're doing, but not in the terms that just, oh, that's what I'm doing, and take it or leave it. You have to explain it so that the other person can actually understand it. And of course, you need to have a strong interest in problem solving. Now, what are the jobs after graduation? As when my children asked me, my two older ones, Dad, what could I study at university? I said to them, it's entirely up to you. There's only one condition. There has to be a job at the end of it. These job prospects, particularly for chemical engineers, are very good. You can go, of course, into research as a representative of a university. I, of course, would put that first. This research can happen at academia, of course, but it also can happen in industry, in research and development departments. You can go into the engineering industries, for example, the process industries. You can make fine chemicals, vitamins, for example, paints, pharmaceuticals. I've already mentioned earlier with penicillin. You can go into the oil and gas sector, or as I think now it's called, the energy sector, because I mean, one thing that we all rely on, our modern civilization, is that there's always a socket and a plug somewhere, and out of it comes electricity, which powers all of our devices. Without electricity, I think our civilization would pretty much crumble. So the energy industry is key in securing our continued happy existence. And of course, food and drink. Some of you may have enjoyed a cup of coffee today made out of instant coffee. Now, if you ever wondered who has made the instant coffee and how has that come about, that is all chemical engineering. You can, of course, also go into finance. Particularly the City of London used to be quite interested in our graduates, because once you have understood how to model something, whether you model it, whether you model a chemical process, or whether you model a financial process or a stock market, the principles are pretty much similar. I would have hoped you would earn your stripes in professional practice with boots on the ground first before you move into management, but certainly the option is there. And there's also the option to move into consultancy to advise companies. The salary is very competitive. It's amongst the highest in the UK. And here this diagram shows that we are second only to dentistry. Now, the Department of Chemical Engineering, in which you're interested in. That's the longest established chemical engineering department in the UK. It was founded in the year that the Titanic sank in 1912, although of course there's no connection with any of this. In the Research Excellence Framework exercise in 2014, the department was ranked top in impact and environment and second in output. We have about between 40 and 50, it fluctuates a little bit, of course, academic and teaching staff. We have around 17 technical staff, and we also have 21 administrative staff. And when you study at university, you will not just interact with the academics who teach you in classrooms. You will interact, for example, with the secretaries who help you with easing your way through the overall process of being at a university, with the administrative processes that are connected with it, registering for certain electives, etc. And you will also interact, for example, with people in our workshops who keep our equipment going, who maintain it, or who even build new ones. Now, what we offer is a 4-year undergraduate Masters of Engineering degree. We do not offer a 3-year bachelor's degree. We only offer a 4-year undergraduate MEng degree. Our intake is around 140 undergraduates per year, and we have around 800 applicants each year for these positions. So you can see that we're heavily oversubscribed, and we are, I think, for us in the lucky position that we can be selective in what candidates we invite to study with us. Our female contingent in the student population is around 35%, which is average for engineering degrees. Of course, we would like it to be a lot higher. Ideally, it should be 50% or a bit above 50%, just going simply by genetics. And we have seen over the years, though, a very gradual increase. So over the last 10 years, this number is slowly gone upwards from below the 30s to now 35, and it's increasing further, which is very encouraging. We are a very cosmopolitan university. In the department, there are over 40 nationalities represented from all over the world. And in the Times Higher Education World University Rankings, we were ranked 9th last year. And in addition to our undergraduate degree, we also, of course, offer postgraduate education with a Master's of Science degree, and we also offer PhD opportunities, but this is, of course, not the topic today. We'll focus on the undergraduate course. Right, let's have a look at the undergraduate population, and this is the 2019 intake, the nationalities, and you can see that around half of our students come from overseas. About a little bit more than a third, 36%, come from the UK, and about 13% come from the European Union. And here on this graph, you can see from how these, from what different countries these students come from. The majority of the population comes from the United Kingdom, of course, but then the next highest is on the list is China, Malaysia, Singapore, and then the rest. You can see we've literally got the whole world represented, which is great because we pride ourselves in being an international and welcoming university, and we believe this is one of our unique strengths. Because whenever somebody asks me, for example, what is the great thing about working at Imperial, my answer is always the people and the opportunity to meet people who otherwise you would have never met. You wouldn't even know that they existed, because how likely is it, for example, that I personally would travel to Nigeria? Probably I wouldn't. But here at Imperial, I have the opportunity to meet all these people, which is great. Our aim is to graduate the students of the highest quality. And we don't want them to be good engineers. What we want them to demonstrate is technical and professional leadership in successful careers. We want them to be the future movers and shakers, the key opinion leaders in shaping the course of industry on society. Now, the undergraduate courses which are on offer, as said, we offer an integrated master's degree, which is at the further higher education qualification level 7, which is accredited with the second cycle of the Bologna degree. So if you are in any way familiar with the way European universities work, they have 3 years bachelor's degree courses and then 2 years Masters of Science. And so they take 5 years to come to a level, to a master's degree, what you do at Imperial in 4 years. We have the straightforward Masters of Engineering and Chemical Engineering course, which is codenamed H801. Then we have the course which is Chemical Engineering with a year abroad, which is essentially a subset of the Chemical Engineering course. And then we have Chemical with Nuclear Engineering, which is a separate course, but all students essentially enroll in the traditional Masters of Chemical Engineering course, and then they transfer after year 2, where things then start digressing. All courses last for 4 years. They are full-time courses, not part-time. They have in total 240 European credit transfer system, which is a measure of the student effort of that you have to put in. And there's also not just the ECTS, but in the UK, there's also that's equivalent to 480 CATs. Yes, and I just couldn't resist putting that picture in, I'm afraid. Now, our courses are fully accredited with the professional institution, which for us is the Institution of Chemical Engineers. That means once you have studied our courses, you will have met all academic requirements to become a chartered engineer later on in your professional life, if you wish to do so. We were ranked 2nd in the Guardian and 1st in the Times Higher Education University League table. And if you want to find out more, there is a link at the bottom of this slide, which describes where our undergraduate courses, detailed information on our undergraduate courses is kept. Now, I've mentioned already the measure of the student effort, or is the ECTS, and we can translate this into an indicative annual workload. So an annual workload for you as a student would be around 1,500 hours. And you can see here on the graph that in years 1 and 3, about a quarter of those 1,500 hours, that is timetabled, which is a sort of contact time that you spend at university, either in lectures, in seminars, in tutorials, in laboratories, in the pilot plant. More about that in a minute. But the majority is independent learning, and where you decide how you learn. This could be together with your friends in the library. This could be in our own breakout rooms in groups. This could be in a quiet room on your own, whichever way works for you. And that is one of the key things when you study, that you need to find out what actually works for you best. Year 4, the ratio is the same essentially. There's only one difference is what I wanted to point out, that a significant proportion of the timetabled hours in the year 4 are taken up by our capstone project, which is called Final Year Design, where you practice everything that you've learned so far and you design a chemical plant to make a certain product from scratch. Literally blank sheet of paper. You get a brief, this is what you need to do, and then you with a team of 11, 12 other students get together and you simulate an engineering company to design and build that plant. And of course, these are roughly indicative times because they need to be adjusted in reality to your individual learning style. I said that already, whatever works for you. Now, how do we teach and assess? Now, traditional, of course, we do lectures, which lectures is for the whole cohort. All lectures get recorded and made available for revision purposes to students. We also do academic tutorials, which is literally only for year one, where you work in smaller groups with about 6 to 10 students to solve problems that are connected with the lectures. And the idea is that in these academic tutorials in year one, you acquire the skills in order to then solve these problems later on as you work through your degree or by yourself without any direction from input from a teacher. Because the idea is at a university you have to learn how to learn. It's a step into lifelong learning, and you need to acquire the skills that you can be essentially a self-starter with these things, and that's what we try to promote with this. And we have a significant component of project work and design. I already mentioned. We have a loan laptop scheme that in the department that we provide every undergraduate with their own laptop, which meets our specifications. We have undergraduate laboratories, and we also have a pilot plant, which is certainly unique to the university, certainly in London, and it's also not that common for any other universities in the UK to have a pilot plant, which is a small scaled down version of the real deal. So in our setting, you literally get exposed to technology that you will be using as a practicing engineer. The assessment is shown in the table at the bottom of the slide. I said that the degree lasts 4 years, and you can see that in the beginning there's probably a heavier emphasis on examination, like 70% of your assessment is done through exams, 30% is through coursework and practical, and then as your studies progress, the weighting goes more heavily towards coursework and practical, which in the end of at the year 4 is essentially 50-50. And you can also see that the year weighting it's a cumulative degree, it's a modular degree, where each year contributes a certain part to the overall degree outcome. You can see that the weighting of each year increases as you progress through your studies. And that's intentional, because we want to measure the exit trajectory, not the entry trajectory in which you come to us. Now, what do we teach you in the curriculum? Well, it's a little bit like in football. It's a game of two halves, which means the first 2 years deal with core chemical engineering, and the second half is more geared towards industrial practice. So in years 1 and 2, you get mathematics for engineers, of course. I already mentioned that it's quite a mathematical degree, but it's not about for mathematicians. We use mathematics as a tool. It's not applied mathematics. There obviously has to be a heavy chemistry component. We are chemical engineers after all, so organic, inorganic, physical, bio and industrial chemistry is all in there. Thermodynamics, and then specialist chemical engineering subjects, for example, process analysis, which allows you to break down an industrial factory into its component parts and learn what these different component parts do, and then essentially put them back together again in the design stage. Separations is very important, because when you make a product, you always make waste with the product, and you need to separate the waste from the product. Reaction engineering, that's a subject, for example, that I teach, is important, because before anything you can separate a product, you have to put chemicals in contact with each other to react to form a new chemical entity. And in what environment that needs to happen, in what industrial environment that needs to happen, that you will learn in reaction engineering. Transfer processes is also important, because before you can react anything, you need to get there in the first place. And in the real in real plants, Reactors, for example, are not immediately next to storage tanks. So in order to get from a storage tank to a reactor, you might have to have quite a long distance to cover, several hundred meters, for example. So how do you get from A to B before you can actually react stuff? And then, of course, everybody wants to do things safely and reproducibly. So one important component of our course is to understand the process dynamics and control. You will also learn foundation and knowledge labs, where in foundation labs you get taught essential practical hands-on skills that you need to know as an engineer, that you need to be able to do. And then in knowledge labs, you start fusing the concepts from different lectures into a more of a problem-solving environment. And then, of course, you also have the opportunity to work on the pilot plant, where you essentially simulate a shift team of engineers that get set a certain task to start up the plant, to run the plant, to deal with alarm scenarios, to hand over to different shift, etc. And that is what you will learn how to work on a pilot plant. Then year 3 is more advanced. So now essentially the groundwork what we led in year 2, years 1 and 2, we're now going into more depth into some of these subjects. We'll start talking about how to optimize processes, how to get the best performance out of them. You will revisit reaction engineering, but now in a more sort of realistic setting rather than an ideal setting. You will learn how to make particles of certain properties. Remember the coffee, instant coffee that I mentioned earlier. And you will also be learning about integrative modules, about process design, about safety, safe engineering, loss prevention, environmental engineering. Yeah, nobody wants to make stuff and then just dump toxic waste somewhere in the, so we're hoping that nobody will find it. That can't just, is not possible. So you have to be responsible and literally have to design a safe environmental process into your thinking right from the beginning. You also have the opportunity to pursue a subject called I Explore, which gives you the opportunity to stretch your university experience to subject outside of chemical engineering. So you can do, for example, languages in this, you can do business modules, and you can do certain modules from other departments around the university, what they do to broaden essentially, as I said, your horizons and your experience. You also have the option to choose an elective from 6 on offer, and they could be, for example, on membranes, which help separating things, on nuclear engineering, biochemical engineering, carbon capture, which is quite popular these days, or heat transfer and fluid mechanics. And then, of course, you also do a practical component in year 3, and these are called the discovery labs, where you and your team, a small team of students, you simulate essentially a research team, where you get given an investigative area and say, like, right, this is something where we need to look into. So you guys have to start thinking about what is worth exploring in this, and then you come up with a plan to explore this, and then actually explore and see what happens, and come up, say, with something new. And that is why it's called the Discovery Labs. Now, year 4 is the last year of the course, and that is essentially dominated by 3 things. First of all, you do a research project in the autumn term, where you work in pairs with one of your fellow students, and you are embedded in a real-life research group in the department, working on a real research, and for the autumn term. And your output will contribute to the work of that research group, and you will then publish your output in a research-style paper, which is shown here on the slide. The spring term is dominated by the design project, and I already mentioned that earlier. It runs for the whole term. You have teams 8, 10, 12, depending on the total cohort size, and you perform a full engineering design of a plant from scratch. And some topics what our students worked on in the past, for example, is a sustainable steel production plant, for which they received a commendation from the Institution of Chemical Engineers. They did a semi-synthetic artemisinin plant, for which they also received a commendation in 2018. And then in 2015, they actually won the Sustainability Student Design Award, where two of our student groups designed a biomass into Fischer-Tropsch liquids plant. In parallel to the research project and the design project, you pursue electives. So you can choose 6 electives from around 11 on offer. The exact number changes a little bit for year after year. And where you can pick what you are interested in and what you want to investigate further. So, for example, you can start looking into colloids, you can investigate how to characterize products, you can do advanced process modeling, you can get familiar with how the pharmaceutical industry works, understand biological processes, or get into molecular modeling, etc. Now, we also have a MEng Chemical Engineering with a year abroad. And the way this works is, as I said earlier, you enroll with it in a standard course, and then you can express an interest in participating in the year abroad. And the way this works is there's a competitive selection process, which is run by the department. You need a minimum of a 2.1 upper second class degree performance or 60% plus over the first 2 years. That makes you eligible. If you want to go abroad into a non-English speaking country, then you need to be proficient in the language, and then you can apply for certain placements, and you fill in a form, and then you get interviewed, and then the panel decides whether you can go on the year abroad. To spend the year 3 at a partner university. For example, you can go to Europe. We have arrangements with universities in France, Germany, Spain, Netherlands, Sweden, and Switzerland. You could go, for example, to Australia or Asia, Melbourne, Sydney, Brisbane, Singapore, or you can go, for example, to America, in the US, California, Carnegie Mellon, and MIT. The key difference, I suppose, with our year abroad to other year abroads is that this doesn't add to your total of study time. So it's a tailored study program, and we carefully selected our partners so that their study learning outcomes in year 3 match ours. So that when you come back from the year abroad, you will rejoin your original cohort and you will graduate with your friends and mates who started studying with you. Now, some components may have to be deferred to year 4. So that may be some small rearrangements. For example, when your friends in year 4 do electives, then in year 4, for example, you may do some of these electives in year 3 in the year abroad, and then you may do some of the core subjects in year 4 when you come back. We also have the MEng Chemical with Nuclear Engineering course, which is run jointly with the Mechanical Engineering and Materials Department. That leads to a full chemical engineering MEng qualification. So you are very well equipped to work in the nuclear industry afterwards, but you don't have to. Okay, you're not getting pigeonholed in any way. It is, as I said, the basis for successful employment in the nuclear and the related industries, but you can also work with this degree in other industries as well. The first 2 years are part of the regular course, H801, and you transfer into the nuclear course after year 2. The way this works, that then core specialty courses replace certain electives in year 3, and you have then 3 electives in year 4, including the iExplore. Now, we pride ourselves on our caring environment and pastoral care and transferable skills, and probably as as a parent myself, this might be probably more addressed maybe to the parents listening to this video, is it's when you leave your home, and I call my children my most prized possessions. Of course, they're not possessions, but my maybe my most prized and achievements in life, really. If you let them leave your home, you save them out from your home into a new environment, which for some, and particularly for international students, is not just a couple of hours away by car. It's a couple of hours or more than 12 hours away by plane. So it's a big step to move into this entirely new environment. So your child, and forgive me for calling the prospective candidates still children, to us as parents, you always remain children, right? Even I'm well over 50 years old now. I'm still just a child to my parents, believe me. It's important that they're being looked after. And so we have a system of personal tutors, which means that you have one academic member of staff gets assigned to you, and this person stays with you for the whole 4 years of your study. And this is essentially the first port of call for anything at university, whether academic questions, whether it's life questions, etc. It's somebody to talk to. We also have a well-being advisor in the department who can help with staying well, staying healthy, and she is also organizes events that because it's as I said, if you move into a new environment, first of all, probably you don't know anyone or hardly know anyone. So how do you get to know people? And find out, how do you make friends, contacts? And so our well-being advisor creates certain events where you can meet people and then actually start doing stuff together, which doesn't necessarily have to be always about work and studies. We keep a close eye on progress. So if a student, sometimes things just don't go so well. Because we are keeping a close eye on it, then we can step in and we can offer remedial tutorials and extra help, for example. We also offer mentoring sessions, which are part of our, they are not necessarily, something that appears in your transcript as an academic subject, but is an essential part of the overall journey at a university to pick up skills, life skills that help you later to secure jobs in your professional career. We have the option for a personal development plan where you can work on your personal interactive skills, for example, under the advice of your personal tutor. We offer peer feedback so that your peers can tell you, well, this worked well, was great what you did, here you can probably improve a bit. And we also have a very good professional skills workshop where how do you write a CV, for example? How do you write a good CV? How do you write a letter of application? How do you prepare for an interview? What is the interview process in general for jobs? And how do you go best about preparing for it, for example? That is all part and parcel of our offering. Now, just a few short words about research. Because Imperial is a research-driven university that is world-class research at Imperial, and this is what the department does. On the slide, I don't want to go through each of these individually, but you can see that probably a big component. For example, multi-scale computational chemical engineering, multi-phase transfer processes. Big component is computational engineering, which is process systems engineering, was actually pioneered here in the department, which is now essentially a standard in the industry. But we also have a big component of experimental work with creating new materials, new membranes, to separate solvents, for example, and the new crystals, generate new crystals, new delivery mechanisms for drugs, for example, new ways to generate energy, environmentally friendly way, etc. I think what is of interest to you, first of all, you can certainly go on the internet and find more about these research themes, but also that undergraduates can get involved in research literally from year one. If you're keen on that, if you're interested in that, in a research environment, there's always work to do. Colleagues would be very happy to have you. For example, I published several papers together with undergraduate research students who did work with me on our research and some research areas. Now the admissions process. Now the minimum requirement entry is 2 A stars and an A. You know that, I'm sure most of you know that already. We need an A star in maths and chemistry, and an A can be in physics, biology, economics, or further maths. That's our minimum entry requirement. We offer at the minimum entry requirement, but typically we also offer, for example, not just at 3 A levels, but at 4 A levels with 2 A stars and 2 A's. If you are studying not for A levels in the UK, but for example for the International Baccalaureate, we require 39 points minimum and 7 and 6 points in core subjects at higher level for maths, chemistry, physics, biology, and economics. And a typical offer would be 776 at the higher level and at 41 points. If English is not your native tongue, then we require a GCSE, in English in B, a 6 or equivalent. I'm sorry, that actually applies to all of us, not just whether English is your native tongue or not. We do require a GCSE in English at B or 6 or equivalent. And if English is not your native tongue, we also require a certificate, essentially, that demonstrates your proficiency in the English language. When we do make admissions, we take the personal and the school statement into account, and then we shortlist people for interview here in the department, or we also offer the opportunity for with Skype interviews, essentially for people who can't make it. And then the interview that gives you an opportunity, well, for you to have a closer look at us, because as part of the interview, you essentially spend an afternoon with us. We give you a tour of the department, the university, you meet our students, and of course you meet our staff. And then you have an interview where you get to know one of our members of academic staff that will probe your understanding on scientific subjects a little bit. And then afterwards we make a decision and whether we should make an offer, extend an offer or not. And the applications to admissions ratio is roughly around 5 to 1. And if you have any more detailed questions about admissions, and particularly, for example, if you do not study for A levels and for the baccalaureate, but for another academic qualification at equivalent to A level, and what exactly do I need to meet in order to qualify for entry, then these people are best placed to provide advice there. We also have the option of scholarships. For example, there is the Imperial College Bursary, which is for home students, and which is for living cost support up to £5,000 a year, which is means tested. Then there is the Imperial College President's Scholarship Fund, which you can apply for, which is scholarship for candidates with exceptional academic promise, which is for £1,000 a year. And then we have several chemical engineering scholarships for home students, which is means tested, so which are sponsored by various people from industry, for example, or private individuals, and you can see the amount and what they are. We also have up to 10 access scholarship, they're called, for students from a widening participation background. And these are to between £6,000 to £8,000 a year. And there are also one-off awards, for example, that for a certain activity or winning a certain prize, or qualifying for a certain framework or the Dean's List, etc. And if you want to know more about this, the internet address is given on the slide. And that brings me to the end of the video. I hope you're still bearing with me, and I want to, of course, thank you for coming so far with me, and listening to the video. I'd just like to close with referring to a few more information sources that can give you an indication of what it's like to study at Imperial College. If you have an opportunity to talk to students, please do so. The best information about what it's like studying at Imperial, you always get from the students directly. I'd like to mention that first-year students are guaranteed rooms in halls. We have fantastic sports facilities. Imperial is at the heart of London, one of the great capitals of the world, with lots of things to do in London. You can find out more about Imperial with these email addresses. We have a very active student union, and there's also more information about the bursaries and widening support available as well. And at the bottom of the slide that's our internet address if you want to know more details out about the department that you can see here. So I would like to thank you very much for your attention. I hope you enjoyed this and found it informative, and this is the end of the presentation. Thank you. Goodbye.